Welcome to Unit 9, Designing and Implementing GIS for DRR Programs, the final unit in this GIS for Disaster Risk Reduction course. In this section, we'll explore a hypothetical community and walk through the process to design a modest, sustainable, and effective disaster risk reduction program using geospatial tools. Let's look at the process steps necessary for a successful project. We need to define the scope, objectives, and authorities to ensure we have what we need to execute. We need to build a community. We need to compile a hazard profile and select the hazards for this study. We need to delineate the hazard areas. We also need to compile the community physical assets and the community socioeconomic assets. We need to perform the risk analysis. We need to communicate and plan that communication carefully. We need to plan for maintenance and sustainability of the effort. Our community. For this exercise, we'll be looking at the island of Solfatara. It has a population of about 80,000. It's a short ferry ride from St. George's on Grenada in the West Indies in the Caribbean. St. Stephen is the primary city on the island of Solfatara, though 4 other major towns are spread around the island. The city's economy is fueled by ecotourism, banking, government, transportation, agriculture, distilling, and a large university. Solfatara is largely agricultural and land use and is on volcanic soil. Tourist destinations include small areas of private coves, hot springs, and views of the inactive, though not dormant, stratovolcano near the center of the island. Large areas of the island are uninhabited due to their steep and unstable terrain. St. Stephen's is a member of SEDIMA, the United Nations, OAS, and CARICOM. Following a significant disaster on a nearby island, city managers decided to make a best effort with available funds to assess their risks to natural hazards. Having participated in an earlier OAS-sponsored hazard mapping effort for hurricanes, they were generally aware of some of the risks, but many other hazards were not well studied. Urban growth has been largely stable for 20 years, except in some sprawl up the adjacent hillsides. Understanding that this is a process, the government of Solfatara decides to initiate a process of employing GIS for improved risk awareness. So we need to define the scope and objectives here. We have the authorities already established, as this was set up by the government. Having limited funds and growing competency in GIS, the nation decides to do a modest effort to help them prioritize where more detailed studies and investments should be made in the future. The effort will be pursued with 1 full-time staff member for 6 months, in-kind contribution from government, and $10,000 US dollars for miscellaneous expenses. The objective will be to identify critical infrastructure at risk and to prioritize that risk for mitigation planning. Outputs will be static maps and tables showing each hazard and an all-hazard summary report with enhanced GIS data for assets. Community building will start out with communications planning to understand how we want to reach out and what we want to say to motivate our partners or our potential partners. We want to reach out to civil society, commercial, academic, and press organizations. We want to perform outreach to leaders in these organizations, gauge their interests and their availability to help. We want to employ the following 7 principles in your plans and actions. Design for evolution, open a dialogue between inside and outside perspectives, invite different levels of participation, develop both public and private community spaces, focus on value, combine familiarity and excitement, and create a rhythm for the community. Partners identified and agreements drafted and signed with the following organizations. The St. Stephen's Red Cross Disaster Society. They'll bring disaster expertise, volunteers, and connection to Federation and other national societies. University of St. Stephen's Geography Department will bring GIS expertise and external linkages to the universities in the United States. St. Stephen's Ministry of Health will bring health facility data and linkages to PAHO. The St. Stephen's Chamber of Commerce will bring business information, advocacy, and possible financial resources. St. Stephen's Ministry of Statistics will bring demographics and referential GIS data layers. SEDIMA, the Caribbean Disaster Emergency Management Agency, will bring disaster management expertise, case studies, best practice, external partners in the United Nations, donor governments, and other islands. So this table shows the potential roles of each organization here. The Solfatara National Disaster Management Agency is the primary partner in several roles. They take a leadership position. The Red Cross is highly active in vulnerability mapping and vulnerability assessment. And the SNDMA will manage communications as well. There's secondary partners with SEDEMA on the DRR front, the Red Cross and SEDEMA for hazard research, the university for modeling, OpenStreetMaps and external universities for vulnerability mapping, and the Ministry of Statistics and Utilities for vulnerability inventories. So in considering our data model, we go back to the initial statement from the government that said this would be a very simple sort of screening activity, a very high-level effort, and will not get into a lot of detail on specific impacts on these assets, only an identification of whether they are impacted or not. So we'll be doing a binary study. Only the assets and their locations need to be in the data model. We don't need to have a lot of information on fragility and things like that. With time and resources, adding economic and livelihood data to the assets would be useful, but it's beyond the scope of this effort. Systematic data collection from OSM will ensure the data is widely available in its basic vector form to anyone who might be interested for this and other uses. Now we need to compile a hazard profile. We want to understand which hazards are most worthy of our study given our limited resources. So hazard profiles are an assessment of what hazards can be expected, their intensity of impacts, frequency, and general spatial distribution. We're not going to deep dive here, but it's important to know these things in order to select which ones we should study. So for sources of information, we're going to look at least historical documents, archived newspapers, reports, databases, and books, experiences of senior citizens in the community, geological studies if they exist, and the informed imagination of experts. This last point is kind of key, as you don't want to be limited by what has happened in the memory of those who live on the island. You want to be able to consider rare scenarios that could cause significant impacts. So in compiling the hazard profile, we look at the MDAT database. And we find that there were 6 hurricane disasters in and around Solfatara since 1900. In 1972, 44 were killed, and new reporting from the same time described a range of mechanisms, including surge, wind, and river flooding impacts in the city. There's been some volcanic eruptions. Apparently, the island was named by Christopher Columbus himself, who in 1497 observed a small eruption. Another one was recorded in 1882. It was reported in local newspapers and ship logs. Moderate eruption in 1925 was observed and well documented. Ground shaking and ashfall occurred in Solfatara, but 4 closest towns were destroyed by pyroclastic flows. The area is now a protected nature reserve. Geological record confirms the city is built on historical flows and deposits suggesting the potential for revisit and other related volcanic hazards. For earthquakes, moderate ground shaking has been long associated with volcanic activity and not tectonic-based events. Historical analysis records some damage to poorly constructed buildings and some panic resulting on fear of major eruptions spawned by informal circulated rumors. Flood. Occasional extreme rain events have caused moderate brief flooding in the low-lying parts of the city that have been left as open space. Land use in the watershed has been fairly consistent, but the urban environment additional impervious surface development may lead to flash flooding. Landslides. There's limited historical record within the city, but sprawl up the hills and their geology may be cause for future concern. There's no records of tsunamis in this region. A major urban fire occurred in 1845, and the city was rebuilt with broad boulevards and fire-resistant materials. Though the city has a large forest canopy, there's no record of or little threat of wildfire. Storms. A large number of storms and squalls have taken many lives on land and at sea and have caused occasional floods, small landslides, and wind damage. So the first thing we want to do is sort of triage these different hazards, and based upon their frequency and their likelihood of returning and their impact on the community. And then you can just simply add or multiply or do some mathematical process to see what you like. In this case, we're going to add. So we have earthquakes with a likelihood of 2 and an impact of 2. They're not expecting catastrophic earthquakes, so they sort of hit the middle of the road with a priority score of 4. And you can look down the list and see, with the highest being hurricane, volcano is pretty high based on its impact level, and so on. So to prioritize extreme events potential here, we look at historic disasters. They're easier to research than extreme hazard events as they impacted people and are more noteworthy and thus better documented. Many disaster types are really compound disasters made up of a range of hazardous elements. When studying the disaster history, it's important to try to get the specific mechanism of damage and injury and break it out. Focusing on the hazards keeps the focus on the mechanism, not the historical events, and provides a more accurate lens for protecting a community. And by focusing on the hazards, I mean these events where the hazard didn't turn into a disaster, but still occurred. So a volcanic eruption where everybody was evacuated still counts as a pretty hazardous event. Mitigating a specific extreme hazard type can take the punch out of a number of disaster types. So in this case, for example, landslides are represented in many different types of events, and therefore mitigating landslides might have take some of the potential for damage away from these different events. So looking at this table, you can see that many of these different events can trigger these specific hazards here. So you see an earthquake can cause a river flood, a landslide, and ground shaking. Typically, landslide and river flood are together because a landslide can block a river and cause a river flood. So if you're wondering how an earthquake can cause a river flood, that's how it does it. Volcano, again, has a lot of potential, some very unique elements to it, especially a pyroclastic flow. Hurricane is made up, in this case, of 4 different sub-hazards. Tsunami has a couple, and so you can see how that plays out. So we look at these numbers, and we see that the river flood and landslides are the most frequent specific hazards that play out. Okay, so that for hazard prioritization, this is a model that's as good as some, could be better. What we have here is the number of extreme events under likelihood here that matches the number from the previous table where we just sort of ticked off where they could occur within the hazards. Then the middle column under likelihood shows the number of recorded events in the disaster history context, and this is hazard events, not necessarily disaster events. Then we're going to look at the trend here, and we've just simply done this with plus minus equal. In this case, there's no minus, but the trend we identified was they were positive for coastal flood as people were moving there, river flood as impervious surfaces were increasing, and landslide as people were moving and building homes up the hillside. And we know that volcanic hillsides can be a little less stable than other geologies. So if we look at the intensity of impact potential there, we can see get some indication of the potential level of impact. But then if we look at prioritization score, where we multiply, in this case, the events by the intensity, the likelihood of events by the intensity, we come up with a number that can be used to help prioritize our actions here, our decision. So in this case, we've got a lot of river floods, but not a lot of intensity, but enough to concern ourselves, especially the way they're trending. We've got a number of landslides, and the way they're trending as well is significant. Some interesting things here. We have pyroclastic flow. That's got a 3 intensity level, The problem with that is there's not much mitigation you can do for pyroclastic flow, so you pretty much have to evacuate. There's not, so well that one. Fortunately, there haven't been that number of events, but the intensity would be off the charts. But there's not much you can do except get out of harm's way. So that one is probably not worthy of too much emphasis in terms of mitigation other than early warning. So here's our findings, sort of teased in the previous slide. We selected landslide. It doesn't have its own notorious history, but it relates to many disaster and hazard types and is critical for urban growth. We selected coastal floods because, as we mentioned, there's a lot of growth going on there and a lot of seasonal and year-round population lives there. We selected flood as well because of the impervious surfaces within the city, and they can trigger additional events and affect locations where development might occur without good information on the hazard. So it's good to know where the floods are, since they're the most frequent. Part of this is to avoid building in areas that are at flood risk. So we've deferred, and we haven't declined, but deferred on the rest of these, as they may become important in the future. They may be added in the future, but given the budget and the time, we've decided to just go with the first three. So to delineate the hazard areas, again, we'd go and look at the documents and try to get anecdotal information or any sort of maps that show the high water marks or where landslides have occurred or what have you. We'd explore the hazard literature to get an understanding of how these events behave in nature. There's a lot of scientific research available and studies that of landslides and floods and things in similar geographies, and we should go seek those and try to understand what might be happening or might be at risk of happening. We'll seek out GIS information that might be important, such as elevation models, seawalls, levees, dams, water bodies, geology. Now that we understand the hazards we're going after, we can get specific in the data we want to pursue. We want to create new information, such as stream channels, elevation contours, valley extents, watersheds, things like that, landslide susceptibility, as we talked about earlier. We want to seek out those appropriate techniques for GIS and field observations to define the exposures. So, the initial delineation of these hazard areas includes landslides. So landslides on volcanic terrain can have a range of characteristics. In Solfatara, the hills are 300 to 500 feet high, range from low to moderate slope, and are made up of poorly consolidated volcanic deposits. They're pretty well drained internally, though. Landslide susceptible slopes and runout areas below can be notionally identified. Coastal flood. While surges have significant complexity, without the use of sophisticated models, some assumption can be made. On an open coast, a contour can be chosen, and on bays, harbors, and inlets, a higher contour selected as they likely extend higher in those locations. So in those cases, you select, based upon historical precedent, a contour and then buffer it maybe, go another 3 or 4 feet, and then follow that contour around the island, and that could be a risk zone. For flood, rivers usually have been shaping the terrain long before the arrival of man, and their maximum potential extent can often be gauged by careful analysis of the land, taking into account modifications made by man. So the floodplain itself can be fairly visible. The extents where water has room to spread out can be observed, and then obviously those historical findings of where these events have occurred before can be recorded. So cursory landslide hazard delineation technique could be, you could coarsely assess it by studying past events and just seeing the behavior of those events, finding your steep slopes, doing your landslide susceptibility analysis, and underneath those, the identified areas, sort of mapping a runout area based upon the terrain and some ratio of sort of height to play out. There's a lot of factors that go into how a landslide plays out, including the content of water that's in the soil and things like that. So you want to be conservative, which means you want to look to a bigger area and identify the assets that are within that larger area. In the future, again, because of this spiral approach we're taking and the modular approach, we can replace this analysis out with a more scientifically robust effort, but this is a good start. The coastal flood delineation, as I mentioned before, you can start with a historical analysis of high water marks and record those. With a digital elevation model, you can create contours, and you could put a buffer on that contour. So, if the highest elevated, water level was maybe 20 feet above sea level, you could go to 24 feet and then, just use that contour around the island. You can seek partners through SEDEMA to perform a more detailed assessment for Category 1 through 5 hurricanes too, to see there's models out there that could be run. But in this case, we don't have the time or the budget to do that. But the example on the right shows, a storm surge model for Biscayne Bay, actually, that has a number of different categories in it. And here we're showing up to Category 5. So the initial flood delineation is a little bit more challenging than the coastal flood because the slope of the terrain is downhill and you cannot just follow a contour because the water level flows downhill. So first you would identify a prioritized list of streams that have historically had floods on them, and that as a fairly small island, there won't be too many that are at risk. Then we would do, as we've done elsewhere, is seek out information on the extent of previous hazards. So what was the high level, how high did it get during those hurricanes, or during other events? Find those peak levels and record them, both in document and in GIS if possible. You can put in those points and then walk the stream on both sides and just try to envision where the magnitude of water would extend given the changing nature of the river valley as you go. So where it gets tight, it would go higher. Where it gets wide, it would go lower. And again, you'd probably reach out to SEDEMA and say, hey, and try and find a partner to do a more detailed and sophisticated analysis. So at the end, you might want to combine all three of these into an all hazards analysis in order to understand areas that are safe rather than studying each hazard independently. If you're looking for places to site schools or hospitals or other things, you're going to want to avoid all these hazards. So it's worthwhile to combine them into one. All right, one important point is that the products you make, especially in a sort of cursory mode such as this, will look very authoritative. People believe maps when they see them. So you want to make sure on the maps that you put some caveats so they're not misused or oversold. So here's some suggested language that you could use just to make sure people don't use them inappropriately. It's important that these are not left ambiguous as they can be misused. So for the compilation of physical assets, in Solfatera, GIS is not well established, except the utility companies, and they feel very proprietary about their data, so they're not willing to share all of it, but they may share some. We'll use university partners in the U.S. and OpenStreetMap to create vector geometry and have our Red Cross volunteers do the field surveys to complete the attributes. The utilities will be provided by the water utility, and the electric utility will provide some minimal basic information. So here's a basic compilation of physical assets and the sources where we'll get them, and I've broken them up by geometry and attributes because in some cases, as you'll see, they're different. So we're going to rely heavily on OpenStreetMap to trace and create this base road network and the different buildings. Now, basically, from the OSM, from the perspective of people digitizing in OpenStreetMap, they will just be digitizing buildings, so they won't know whether they're medical facilities or municipal or what have you. So it's up to the Red Cross volunteers to go out and add that information. The socioeconomic assets, including population, economy, and livelihoods, they'll be analyzed in aggregate form at the parish level. Then we'll use data from the Ministry of Statistics, as well as Columbia University for population, because they have a distributed population data set. The Ministry of Statistics will have the population at the parish level, but this GRUMP data, and I encourage you to click on it and go investigate it, it has distributed population in a raster format that can be more useful for some studies. As we mentioned, this is a binary assessment, so we're basically seeing what assets are in hazard areas versus or potential hazard areas, or are clear of hazard areas. So because there's a lot of imprecision in this, we're not necessarily going to be focusing too much on discrete assets, but we're going to be looking more at aggregation of assets. Now, in some cases, there's categories where there's only one asset, so we will not be totally bound by the aggregate thing. But the thing about using aggregate assessments in low confidence studies like this is that the law of averages will balance out. So some things will be included in that shouldn't be, and some things will be left out. And over the whole study area, these things can balance out a little bit. So this will reinforce the findings of the hazard profile and provide further justification for enhanced detailed studies, as we identified in each one of them would be advantageous. So it may not suggest mitigation actions because of that lack of precision as well. It could be that the hazard area doesn't extend all the way to where the asset is. So it's just a starting point. So here's our simple risk assessment results. They're aggregated, although you notice that there's only one medical hospital, so it can't be aggregated. There's one water filtration and one electrical generation station. So each of those couldn't be aggregated. But the rest of it, if you look at it, you can see that 20% of the electrical distribution network is in a landslide susceptible area, 30% is in the coastal flooding, 1% is river flooding. And then if you look over here at all hazard, you'll notice that the sum of these would actually exceed these, but these areas tend to overlap. So you want to avoid double counting and make sure that in doing that analysis that you merge all the GIS data layers into the all hazard layer and then do the analysis with the all hazards so that you don't double count. So you can look down here and see for each one of these hazards the different elements that could be impacted to one degree or another. So the assessment of potential direct impact to assets doesn't fully capture impacts when networks are impacted. So for example, you might knock out 3% of the electrical grid, but it could cut off half of the island. So that requires a deeper dive. As I mentioned, those some assets were identified as 100% impacted because they're a single item. So those specific areas would need to be studied with some level of detail. The all hazard column, as I mentioned, you want to avoid double counting. And socioeconomic data is particularly dubious as it's derived at the parish level, so it's spatially coarse. It needs to be disaggregated further to be meaningful. So communication and planning. For this level of analysis, we want to resist sharing any detailed map products showing risk. There's just not enough precision there to hang our hat on it. So we want to consider generalized whole island products that kind of, instead of using like solid lines, sort of blur things. Share summary numbers and overview reports and dashboards, but don't allow for disaggregation. The assembled information is useful for promoting hazard awareness, early warning, and contingency planning, but requires more detail for actual mitigation-related risk reduction efforts. This will inform prioritization of resources for detailed risk assessments. So to complete this, you'll need to know what these studies cost and prioritize them accordingly. You might consider investments in data that will support multiple hazard assessments, such as detailed LiDAR terrain modeling. This provides a very highly accurate and precise terrain model that could be used in all of the studies that were highlighted for completion, and even those related to the hazards we deferred. So some good data has been developed for the effort. It's probably a little too coarse to be used outside of the study, especially the hazard data. It's very preliminary. But you want to document the data and build metadata. Record how you did it and what it's what it can be used for and how it can be shared. You're going to require additional structural and siting information for future studies. So as soon as that begins to come into focus, you want to develop additional fields in planning the data collection. So you want to enhance that database and begin to plan and maybe even implement some data collection to take it to the next level. But probably not before you have some sort of strategy in place to do those detailed hazard studies. So Solfatera is more risk aware due to your efforts and has started the process that will continue to clarify this risk over time. While not expensive or complex, this initial effort provided useful numbers and raised awareness through the process. The community was involved and must continue to be involved going forward. The next big decision is what to study in detail. The effort's a good measure of due diligence to inform the decision for both the government and the donors that might be inclined to assist. So it's a good tool for highlighting what comes next. Professionalism breeds trust, and trust is key for being rewarded with resources to continue and advance your mission. So do it as well. Perform these studies as tightly and professionally as you can, and demonstrate to your partners that you're to be entrusted with going to the next step. Thank you again for participation in this unit. There is a short quiz that follows. Thank you again for taking the course. I hope you found it useful, and please send your comments to me at my email address, and look forward to the evaluation, the post-course evaluation. Thanks again.